So, welcome student to the next class of Introduction to Nonlinear Optics and its Application. So, today we have lecture number 34 and today we continue the discussion parametric down conversion that we have started in our last class, and then we will start a new topic optical parametric amplification, which is some sort of similar of this parametric down conversion, and this is a special case. But optical parametric amplification in general we study how this second order nonlinearity not only generate the frequency at 2 omega if I launch a frequency at omega, but there is a possibility that it can generate two different frequency, namely signal and idler omega s and omega I, or omega p or omega I. In one case we call it the sum frequency and another case we call it the difference frequency. When they generate, there is a possibility that they can also amplify based on their initial phase condition. So, initial phase, because all these waves should have some initial phase. If they have the initial phase, how this initial phase is important in the amplification process, that we are going to study. So, the thing is, in second harmonic process we find that the second harmonic waves are generating, but in general parametric optical amplification we find that any two frequencies can be generated, and how they are going to amplify, that we will study in detail. So, let us go back to the old slide, the spontaneous parametric down conversion or SPDC. So, where we were studying one condition that if I launch a frequency 2 omega, then is there a possibility to generate two photon of frequency omega and omega, considering that the energy conservation and momentum conservation is valid. So, that means this is a special case. I am launching a frequency 2 omega and I want to generate two frequencies omega and omega, that is coming from this 2 omega frequency, and they are matching, the energy and momentum conservation are still valid. So, the question was, is it really possible to generate such kind of subharmonics? In the previous case we have already shown that second harmonic generation process is valid. That means, if I able to launch a frequency omega in the input, which we call the fundamental wave, then there is a possibility that we can generate a frequency 2 omega, double of that, and we called it the second harmonic generation. So, this is some sort of opposite process or the reverse process, where we launch 2 omega and expect to generate a frequency which is half of that, that means omega. However, the momentum and energy conservation is still valid as shown in this figure. So, this is the old slide I am using as a recap, and the question was 2 omega, if I launch 2 omega, last day we show with the help of mathematical calculation that if I launch a frequency 2 omega, the omega, that means the subharmonic will not going to generate unless we launch some kind of initial wave here. So, the boundary condition suggests that even if I launch 2 omega, if there is no omega frequency at the input, that means there is no field containing omega frequency, then this omega, that means subharmonic, will never going to be generated. That means no subharmonic will going to generate if in the input there is no field containing frequency omega, as written clearly here. However, is it still possible to generate omega if I frequency a field with frequency omega, if I launch a input, if a wave with 2 omega and try to generate the corresponding subharmonic, but at the same time I launch another wave with frequency omega? Because in the previous case we find that it is not going to be omega frequency is not going to be generated unless we launch some kind of input. So, here the second case we are going to study, that in a second order system we launch 2 omega, and along with that we launch omega frequency and try to find out whether we can generate any kind of subharmonic in the output or not. So, the mathematics will exactly be the same, only the boundary condition is now changed. So, this change boundary condition may be generate because of this new boundary condition. There is a possibility that it should generate some kind of subharmonics. So, let us see that. Okay. So, before going to that process, we should clear about the degenerate spontaneous parametric down conversion and non-degenerate spontaneous parametric down conversion. So, these two things are important because right now we are dealing with a frequency omega and subharmonic frequency, a frequency 2 omega and its subharmonic frequency omega. So, why it is degenerate? Because here we can see that 2 omega is splitted to generate two same frequency omega and omega. So, the structure is something like that. I am launching a frequency 2 omega and 1 omega and 1 omega is generating. So, the energy conservation is valid here because here in the diagram, this is the old diagram, the energy conservation shows that if I write this h cross of 2 omega, this is the energy of the photon of 2 omega frequency is equal to h cross omega plus h cross omega. And also the momentum conservation is there. So, this is the degenerate process because we are going to generate exactly the same frequency component omega and omega out of 2 omega frequency. But this is not the case for non-degenerate spontaneous frequency parametric down conversion. In non-degenerate parametric down conversion, we have 2 omega frequency, but it can split to any arbitrary 2 frequencies omega 1 and omega 2 in such a way that 2 omega has to be equal to omega 1 plus omega 2. So, there should be infinite number of combination of omega 1 and omega 2 that you can add to generate 2 omega. So, this is non-degenerate because omega 1 and omega 2 are now distinct, they are not same. So, this is the energy conservation or the energy diagram where we can see that 2 omega photon is split to omega 1 and omega 2 photon, and readily you can find that the energy conservation is valid with this simple expression. And also for momentum conservation, it not necessarily be the collinear kind of phase matching. So, this is a non-collinear kind of phase matching where this is k 2 omega, which is the momentum vector, and k 1 and k 2 are the corresponding momentum vector of the frequency omega 1 and omega 2 field. So, they are not necessarily be in the same direction, but the phase matching can still be possible with this non-collinear kind of structure. So, degenerate and non-degenerate are very important. Degenerate is a special case of non-degenerate spontaneous parametric down conversion. When omega 1 is equal to omega 2, omega 1 is equal to omega 2, then this non-degenerate become a degenerate because they are same, which is equal to omega. So, this is a more general case. Non-degenerate spontaneous parametric down conversion is a more general case, but right now we are studying the degenerate case. This is a special case, and the reason is that we have already studied the second harmonic generation process. So, as a consequence of second harmonic generation, because we have already studied that process, now we extend our study and try to find out what happened under a spontaneous frequency down conversion or frequency up conversion process. What is happening in case of special case of second harmonic generation. So, let us now go back to the next slide, which is the calculation part, and now using this calculation part we try to understand really subharmonic will going to generate or not. So, if you remember the expression of d2 E1 dz square was this, the expression was same that we have used in the previous calculation, only as I mentioned only the boundary condition will going to be modified. So, in the previous case we had the same expression here, the differential equation that we derived. So, the differential equation is shown here, only the thing you should note that a extra boundary condition is added here. The boundary condition is, in the previous case it was E1 at z equal to 0 was 0, but now we modify this boundary condition and saying that E1 at z equal to 0 is equal to some value, and we write this some value as U10 e to the power of I phi 10. This is a non-zero value, this is a non-zero value, and this value is at z equal to 0, that is the electric field containing the frequency omega, that means this at z equal to 0 point. So, we have a amplitude part and a phase part together in this input, and the reason is if I start with the amplitude and phase, then we can understand what is the role of the phase. Not only the amplitude evolution of the amplitude is important, but the evolution of this phase is equally important here. So, that is why these two terms are taken in the input. So, now under this new input condition, this boundary condition rather, we may have a new kind of solution. So, here the general solution is written, this is the general solution of the expression that we have derived. So, d2 E1 dz square is equal to gamma square E1, this is our differential equation, and we have a general solution A sin hyperbolic of gamma z, B cos hyperbolic of gamma z. So, once we have this general solution, next we put the boundary condition. If I put z equal to 0 here, then in the left hand side we have E10, that means at z equal to 0 what value we will going to expect. If I put z equal to 0, this sin hyperbolic term will not be there and cos hyperbolic term tends to 1, and then we will have only b. So, at E10 is equal to b, and this b should be equal to U10 e to the power I phi 10, which is nothing in general I can write. So, this is the amplitude and phase part written, which is our boundary condition as shown here, which we can write in short E10. So, E10 is nothing but the electric field, the complex amplitude of the electric field at z equal to 0, and when I divide this complex amplitude part into amplitude and phase, one can divide this into this. So, in a single equation we can write everything. So, the coefficient b is interestingly now not equal to 0, the coefficient b is not equal to 0. Previously, if you remember the previous calculation, b was 0, because in the input we considered that there is no fundamental or E1 field. So, that is why this quantity was 0. So, b was 0. Now, in the similar way we try to find out what is our A. So, in order to do that, the next thing that we need to do is, this is our now the total field. Instead of b, I now write E10 because b is equal to E10, and then we make a derivative of this quantity. Once we make a derivative of this quantity, we will have the derivative of this, and the derivative of the first quantity gives me A gamma cos hyperbolic gamma z, and derivative of the second quantity gives me E10 gamma sin hyperbolic of gamma z. So, why I am making derivative? Because I am going to use the next boundary condition, and there is a derivative form of that here. So, this was our main equation, and from this main equation, once we have it, so this is our derivative term. So, in this main equation we can see that d1 d1 dz, de1 dz is this quantity. If I want to find out what is the value of d1 dz at z equal to 0, we need to put the value of this equal to 0 and this equal to 0 at z equal to 0 point, what is the value. So, exactly that we are doing here. So, de1 z at z equal to 0, from this equation we can say this is a gamma, because when I put 0 from this equation, z is 0. So, this term become a gamma, and here z equal to 0, sine hyperbolic of 0 is 0. So, this term will not be there. So, a gamma should be equal to, from this equation I can find that it is I omega d divided by n1 c multiplied by E2 at z equal to 0 and E1 star at z equal to 0. So, this. So, now one thing you should note that again we find something which is non-zero. Previously, in the previous calculation, when we put input, there was no input. So, E1 z equal to 0 was 0. Under this condition, the consequence was A and B both are 0. That is why entire thing was vanished. So, the conclusion was we will not going to get any kind of electric field, electric field having the frequency component omega, or in other words subharmonic will not going to generate it. So, now the subharmonic, here we find that with small amount of input value with subharmonic frequencies, there is a possibility that we can amplify or we can generate something out of that. At least the boundary condition, using that boundary condition we find A and B is not equal to 0. That means, there should be some kind of evolution of that subharmonic field. So, now we put the boundary condition here, and then we find that A gamma should be equal to E2 at 0 and E1 star at 0. So, E2 at 0, again we put one quantity, and this is amplitude and phase term. So, U2 e to the power I phi 2 0. I put it U2 to make sure that E2, our valid condition was, our approximation was U2 is nearly equal to constant. That means, there is no change of amplitude of E2. So, that means, U2 is some sort of constant here. So, it is not going to change over distance, mod of U2 is not going to change over distance, or the power of U2 is not going to change over distance. And U10 was already defined, it is U10 e to the power I phi 10. When I put these two things together, then we find what should be the value here in for A gamma. For A gamma, it should be A equal to I divided by gamma omega d n1 c E1 0 star and E2 0. It should be the value. Now, if we remember that it was kappa d omega n1 c was kappa. So, if I put it is 1 divided by gamma into kappa, and if I use the phase amplitude term here, the phase amplitude term gives me U2 U10 e to the power of 1 phi 20 minus phi 10, which is these things. So, we have a phase associated with A, and once we have the A and B together, then I can put this A value here, and here we have already E0, which is our B. So, when I put this, so we will get simply A, this is our A that we have just derived, and this is our B, which we have derived in the previous slides. So, we have a total electric field E1 in this particular form. It looks quite complicated right now, but we will see it is not that complicated it looks. It can be simplified, and when it is simplified, then we have a very nice physical implication out of this expression. So, here we will see that gamma is equal to this value. By definition, we have already defined this gamma before. So, gamma is omega d divided by C n 1 mod of u 2, and mod of u 2 is, so u 2 was defined as, E 2 is defined as u 2 e to the power of I phi of 2 0. So, mod of E 2 is simply u 2, that means only the amplitude part. So, and omega d C n 1 is nothing but kappa, so it should be kappa. So, gamma becomes simply kappa u 2, and this is the term that we have derived in the last slide. So, E 1 is equal to that quantity which is A and this quantity which is B, then sin hyperbolic gamma z and cos hyperbolic gamma z, which is the z dependent part. So, now in this kappa gamma u 2 we can replace this as 1, because here in this expression we find that gamma is equal to kappa u 2. If I put gamma is equal to kappa u 2, so this term, these two term k u 2 will going to cancel out, and we will have simply I u 1 0 and e to the power of I phi 2 0 minus phi 1 0, which is the phase term, then sin hyperbolic of gamma z and u 1 0 e to the power of I phi 1 0 cos hyperbolic of gamma z. So, here we have one term u 1 0, here also we have one term u 1 0. So, the next thing that we will going to do, we are just going to take the common u 1 0 e to the power of I phi 1 0. So, entire term, so this term we take common from both the side. When we take this term common, you can see that there we have e to the power of I phi 1 0 with a negative sign. So, I am taking common e to the power of I phi 1 0. So, that is why a 2 term is appearing to compensate that quantity. So, eventually we will have u 1 0 e to the power I phi 1 0 common, then inside the bracket we have I e to the power of I phi 2 0 minus 2 phi 1 0 sin hyperbolic gamma z plus cos hyperbolic of gamma z. Just slight modification, just write cos hyperbolic gamma z plus this quantity. When I write now exponential term, you can see that this I is now absorbed inside the exponential term, because we know I can be written in terms of exponential, and it can be written as I pi by 2. E to the power I pi by 2 is I. So, we just write this I in terms of exponential and put this term inside this total phase. So, now this term become phi 2 0, 2 phi 1 0 and plus pi by 2 here. Once we have this, then what we will do? We will put a name here called delta. So, delta is something which is related to the phase of E2 field and the phase of E1 field, but phi 2 0 minus 2 phi 1 0 plus pi by 2 is delta. So, now if I put these things here, so we will going to have one expression. So, E1 0 E1 z is nothing but E of 1 0, mind it, this quantity is nothing but E of 1 at z equal to 0, that is the input, multiplied by cos of hyperbolic of gamma z plus e to the power of I delta sine of hyperbolic of gamma z. So, we will have a term like this. Let us see what is the implication of this term. As I mentioned, we have one term here which is e to the power of I0 e to the power I phi 0, and then cos hyperbolic of gamma z e to the power I delta sin hyperbolic of gamma z, and then I say my delta is this quantity. Now, I put delta equal to two different values. In the first case, I put delta equal to 0. If I put delta equal to 0, then this quantity simply becomes E1 z will be E1 0, and then we will have cos hyperbolic of gamma z plus delta is 0 means sin hyperbolic of gamma z. We know that cos hyperbolic of gamma z plus sin hyperbolic of gamma z is nothing but exponential of gamma z. So, if I write in compact form, E1 z become E1 0 e to the power of gamma z. So, this is an interesting term. So, when delta is 0, this kind of phase matching are there. So, we will see that because of this kind of phase relation, we have an amplification. So, with z, if z is increased, then we will find that E1 z will going to increase. So, we will have the amplification of the total field E1. Whatever the value we have at the input, it will going to amplify. That means subharmonic will going to generate. On the other hand, if I put delta equal to pi, then e to the power I delta become e to the power I pi. So, we will have a negative sign here. So, we will get this kind of expression E1 z is equal to E1 0 cos hyperbolic of gamma z minus sin hyperbolic of gamma z. This term is nothing but e to the power of minus gamma z. So, exponentially decay term will be involved here, like it is shown here. So, that means if the phase relationship between E2 and E1 in such that the delta become pi, then we will get an attenuation. That means there the subharmonic will not going to generate anymore. So, we find one interesting thing here, that subharmonic can be generated and amplified if there is a phase relationship between E2 and E1, and this specific phase relationship basically allows the subharmonic to be generated. So, this is a phase sensitive kind of amplification. On the other hand, if the phase is such a way that it can destroy or make these things exponentially decay, then it will not going to get any kind of subharmonics. So, this is some sort of parametric process where the phase is associated with that. So, we find that even subharmonic can be generated, but it depends on the initial phase, and if the initial phase is such a way that subharmonic input is still there, but will not going to generate any kind of subharmonic field because it will going to decay exponentially. So, with this note, let me conclude here. So, in the next class we will start from this point and try to find out more about the parametric amplification, and thank you for your attention and see you in the next class.